always made up of 10 and then 2, so I'm going to write the 1 denoting the 10 first, and then I'm going to write the 2. If I were doing it in a little endian format, I would have written the 2 first, and then I'd have written the 1 first, because then I'd read it from left to right, so, or I'd have read it from right to left. So when I store something in a little endian format, in this case, since I'm using 16 bits, which is 2 bytes, what is important is that the lower order bits are going to be stored first, and then the higher order bits are going to get stored, which means when we retrieve these values, when we retrieve the depth values, we have to flip it back. Does that make sense? Otherwise, you will not get the right number. You have to flip it back and then read the whole value, which we'll look at in the demo. So this is just an example. This is just a slide that illustrates little endian format. So that's basically all I wanted to talk about depth in the slide. So it basically still returned as imageframe.image.bits, and it starts at top left just as before. It moves from left to right and top to bottom just as before, but instead of representing RGB values per pixel, it is now representing distance values per pixel. Does that make sense? Okay, so let's go in and do the demo. So I'm going to come in, I have this exact same code as before, and I'm just going to modify this to, instead of just doing color values, so now it does depth values as well. So which means instead of just reading the RGB camera, now I'm going to read the depth camera as well, which is actually the more interesting part of the game. So the first line that I wrote earlier about initializing or instantiating my OneConnect still is going to remain the same, right? Nothing really changes here. The next line, where I initialize the connect, is going to change a little bit. Instead of just saying use color alone, now I'm going to use the OR sign and chain another option of saying either use depth or use depth in player index. First of all, I'm just going to say use depth. Let's just use depth first and see what happens. Then we'll come back to depth and player index. This one line now, what it's now doing is it's initializing the driver subsystems, the software subsystems for both the RGB camera now through the use of use color, and also the depth camera with the use of use depth. Right? So now both subsystems, the entire camera subsystem in the Connect will get activated. The next line was where I was opening the video stream, right? So now what I would do is, apart from just opening the video stream, I would open the depth stream as well, because again, remember, the depth stream is the feed from the depth camera. So I'm going to open it, and most of the options are going to be very similar to what we saw earlier, except now instead of image stream type.video, I'm going to choose image stream type.depth. And then instead of, actually the pool size was 2, and I think 2 is still a good pool size to go with. And instead of a resolution of 640 by 480, a resolution of 320 by 240, since that's the default. And finally, image type is going to be image type dot. Instead of color or color by UV or color raw, I think it's going to be depth, because we're pulling depth data. But you see how similar the code is, right? This line and the previous line are super similar. You're just changing 2 values. Instead of dot video, you get dot depth, and again, instead of dot color, you get dot depth. That's it. Everything else, and the resolution you end up changing, because the default resolutions are different. And once you do that, that's it. Then the next thing we did was basically create a new event handler for video frame ready. Now I'm going to create a new event handler for depth frame ready. Right? I'm just going to say plus equals tab gives me a new event handler, and I'm going to empty it out and start coding. Now you see, like before, I can do exactly the same thing. In fact, this line I can take and just copy as it is, because E right here will still send me an image frame, right? And image frame dot image will still have the actual data. So you know what? Let me do this. I see image is of type planar image. On the left, you can see that it's planar image frame.image. So I'm gonna store it in something of type planar image. Planar image p image equals iframe.image, right? I've grabbed the image. But here's the thing. I probably, see in the previous case, since all of the data that was coming in my image was just RGB, I could just take it and throw it directly into an image source. In fact, you know what? Let me show you something. Let me just copy this and paste it here. Let's see what happens. Instead of image1.source, I'm going to say image2.source, but let's make sure there's an image2 here. And I come in here and drop another image. Where's image? There it is. Okay, I have this other image. So this right here is image2, right? If you look at the source code, here's image2, right? So this is image2. So I now can say image2.source equals bitmap source.create iframe.image.width. Well, iframe.image is p-image, so I'm just going to use p-image instead of iframe.image. So p-image.width, p-image.height, -6 would be the same. Pixel formats, PGR32. We'll come back to that in a second. The stride is still going to be p-image. Or the data is still going to be in p-image.bits, and the stride is still going to be p-image.width times p-image dot bytes per pixel. Right, so this is exactly the same as before, in fact. So here's my problem now. My only problem is I know that the data that's coming back is still in bits. Everything is fine, but the data in bits, each data segment now isn't 4 bytes long. It's not a BGR. It's 2 bytes long. It's a 16-bit structure, right? You please saw that, right? And here's the problem. If I run this the way it is, let's just run it and see what happens. If I run this the way it is, you see how there's an exception? It says value does not fall within the expected range, because it's expecting a 4-byte structure, and then it's reading 444 bytes at a time, but then it finds out that halfway across it just terminates, because it's for the entire length it's supposed to be 2 bytes long, but now it's reading 4 bytes long, and so it's halfway through the process it finds that the array is empty, and so it basically says value does not fall within the expected. So it's freaking out, right? So let's look to see if there's some 16-bit values in here, right? So all of these, this is a 24-bit value, this is a 32-bit value. Let's keep coming down. There's actually something called gray 16, which is a 16-bit value, right? So let's try and see if we can run it now. And you'll find that you can actually run it. I mean, it is actually running, and you'll see that it's actually displaying some data. In fact, if I move my hand, are you able to see it's doing something? Like if you look at this window in this region, I can see some movement, but it's all so dark that you can't really make anything out, right? And you know why that is? So the gray 16 scheme is used to denote brightness values across 2 bytes, across 16 bits, right? The brightness values it expects are a number between 0 and 64K. That's 2 power 16, right? You know how RGB, each channel expects a number between 0 and 255, because it's 8 bits. Similarly, gray 16 expects a gray or a brightness channel, or not a brightness channel, a grayscale channel between 0 and 64K, 65,535, right? Now here's the problem. The data that it is trying to encode is right here, right? The problem with the data it's trying to encode is that the data is only 12 bits long, right? The depth value is only 12 bits long, which basically means that the maximum number that can be stored in the bits field is 2 power 12, which is 4096, right? So what we are doing is we are showing an image where the maximum ceiling limit is only 4096. And imagine doing that in a gray 16 format where 64K is white, full white, 65,535 is full white, and 0 is full black, Now, if your ceiling is only 4,000, if all the values you supply are topping out at 4,000, 4,000 is still significantly smaller than 64,000, and so most of the image appears dark. Does that make sense? Right? Which is what's happening here. You'll actually be surprised. There's actually valid data here. It's just all appearing dark is what it is. Now, the fact of the matter is, though, that instead of trying to display raw data like this, and most of it appearing dark, if you want to represent this data in an image, you have to do one of two things. One, let's take this and amplify it enough to store it to make sense in a 16-bit structure, like Ray 16. Or, number two, let's come up with our own heuristic, right? Instead of displaying it as it is, let's create a new byte array and code it with RGB values based on distances. So let me explain what I mean by that. But before that, let me show you the data that's in p-image. You know how we saw the data that was in iframe? We saw the values were, RG or BGR and blank, BGR and blank. Let's actually see what's in p-image before we proceed any further. So let me set a breakpoint here. Run this. And you actually see we hit the breakpoint. Now let's examine p-image. P-image, as before, is just a long array of bytes. Now, except this time, it's 153,600 long. Let's find out what is the significance of 153,600. 153,600 is just 320 times 240, which is the resolution of the image, times 2 bytes per pixel. Is 153,600. Does it make sense? Okay. Now, that is the 153,600, which is this. Bytes per pixel, as you can see, is 2, heightened with our 320 by 240. If you look at the data, though, you'll find that, well, it's all turning out to be 0 because I think, okay, here's the thing I also want to mention. Kinect, like we said, can only detect between 850 millimeters and 4,000 millimeters, right? Any distance under 850 or any distance over 4,000 gets represented as a 0, right? So if the Kinect's here and the extreme corner that it's looking at is too far out for it to make sense, then it's going to show it as a 0, right? And that's what you're seeing. In fact, it's very common to run a program and see a huge bunch of zeros before you see anything meaningful, because this means that the top 2 or 3 rows in that image are all either too far out or too close in. And so when I do a demo like this in an audience like this, where the top rows are sort of here, you're going to see all zeros because Kinect cannot see anything within 4 meters. So if you keep going, you might have to wait a little bit actually. Yeah, this is going to take it, because right now it's sort of processing. And remember, each row is 320 bits long, or 320 pixels long, and each pixel takes 2 bits. So each row has 640 array elements, so which means we're still in the second row of pixels, right? So as you can imagine, there's quite a long way to go before we'll see any data. But when the data does show up at some time halfway through the image, you know what, let's actually do this. Instead of doing this, let me turn it towards myself. Let me just show my hand about a meter away so it actually sees something early on. Or let me just stand like this, it'll see only me. And now let me run it again. Okay. And now, if I look at iframe, open this, not iframe, p-image, open this. You see how early on there's data? So that was a good use of time instead of waiting for it to scroll through, right? Okay. So here's the interesting part, right? You'll actually see that the values here, you'll actually see proof of being little endian, right? So obviously because the fact of the matter is that you have a 12-bit structure. If it were big endian, the first byte would have had 4 bits, and the next byte would have had all 8 bits, right? 4 plus 8 bits. But because it's little endian, it's flipped. So the first byte will have full 4 bits, and the next byte will only have, or the first byte will have full 8 bits, the next byte will only have full 4 bits, right? Or the remaining 4 bits. Which means the first byte can range between 0 and 255, but the next byte can only range between 0 and 2 bar 4, which is 16 or 32. 2, 4, 8, 16, yeah. So you'll actually see that the first byte, every even byte, 0, 2, 4, and so on, will range between 0 and 255. The next byte, 135, will only be between 0 and 16. So you can see that over here. But this gives you a general idea of the data that's coming back. Again, these are not color values, these are not grayscale values, these are raw distances between connect and what it's saying. So I think what makes sense to do is, instead of trying to render this directly into a color image, let's actually try and do something else. Let's try and do a small computation called, say, calculate distance or something, where we pass it p_image.bits. Right, so what I'm doing is I'm taking the whole array and passing it to this method called calculate distance, which doesn't exist. So Visual Studio says that I can generate this, which the step for it is generated here, so I can come in and start working on it. Now, let's identify the approach we want to take. The depth frame, since it returns distances, let's basically do it this way. You know how I deleted this code block here that was actually showing a bunch of, okay. You see this code block here, it actually displays an image, right? But instead of gray 16, let me just do PGR32 like before, but instead of p_image.bits, let me leave it blank for now. But what I want to do is this. Like before, I want to display a color image, but this time I will create my own color image, right? Based on the distance value, let's generate a depth histogram, if you will, and display it on the screen. So let's come back and revisit this code section after we are done with the computing distance aspect of things. So what I'm going to do now is I'm going to take the data that gets returned, which is distance images, and calculate the distance for each pixel on the image. So I'm going to do something like this. I'm going to run a loop for int I equals 0, I less than p_image dot bytes, dot bits dot length, right? This basically is going to run through the distance of the array, and I'm going to have it skip by 2. So what I'm going to do is I'm going to grab every alternate byte. Now the next thing I'm going to do is I'm going to call a method called getDistance, which is what we did before. But now I'm going to pass p_image dot bits of I and p_image dot bits of I plus 1. So what I'm doing is basically I'm passing it the successive 2 bits, which means for each pixel I'm sending it the 2 bits that represent that distance. Now in my getDistance method, what I need to do, this is my getDistance method. It's taking byte p. I'm going to change it to call it byte p1 and p2. In getDistance, what it's getting is it's getting 2 bytes. What I need to do is, since it's stored in a little endian format, I have to flip the order and read the value back. So I'm going to write the source for it, and we'll talk about it in a second. I have bytes p1 and p2. I have to basically combine them together. The way I would combine, how would you combine 2 bytes together? You would use an OR, right? So if these were stored in big endian, I'd have done this, P1 or P, right? It's basically, you know, the order is fine, P1's first and then P2's. But because this is stored in Little Endian, I want to take P2 and put it ahead of P1. And the way you put something ahead is by left shifting, yeah, exactly. So let me shift this by 8 to move this one full byte ahead, and then let's combine it. And funnily enough, let's see if this combines. Okay, I need the semicolon. What is that? Here. Okay, build actually succeeded. So now, this one line right here basically takes 2 bytes that are stored in Little Endian format, makes the second byte get in front of the first bit, adds them together, and gets the distance back. And let's actually, at this point, return distance, which let's collect here. Int distance equals whatever. And you know what? Let me just type some random line of code here, set a breakpoint here, or not breakpoint there, a breakpoint in the next line, and then let's compute distances. Okay, what's the build error? Okay, it's because I've already used I up here. I'll call this J instead. Okay, I cannot replace it with a void. Okay, here's the problem. I'm returning a void. I can say int. Okay, how about now? Great, it works. So let's set the breakpoint here. Let's run this. So we stand before the connect. And now, for I is 0, which means for the first pixel on the top left, right? It's returning the distance as 2,505, which is this what it's, I think, seeing me or something. I think it's seeing this. And this distance is about 2.5 meters. Would you agree? Yeah? So you basically see that our computation seems like it is working. So if I keep running, let's keep, see 25, 23. And then as it keeps reading the frame, it will come to me, and sometime soon the distance will actually reduce. 2,542. Whatever. So you basically, we're seeing that the code actually kind of seems like it's working. So the distance we're going to get is going to range between 850 and 4,000 ideally. So let's do this. Based on the distance value that we get, let's create a new byte array filled with RGB values and display it on the screen. I'm going to write 4 or 5 lines of code first, and then we will examine it in a second. Because I'm really bad at writing code and talking at the same time. So I'm going to say int color index 0. BGR, blue, green, red, okay. Blue. And offset. Okay, so BGR, and now what I'm going to do is just create a new array, poly array, color, equals new byte array of, I think it's going to be p image width times image.height. I'll explain this in just a second. What is this going to be? Oh, yeah. So sure. Okay, how do you create a new byte array? Basic C#. Anybody here that's done C#, how do you create a new byte array? Sorry?
Just add a new byte to the library.
Right, this should work, right? Any creation, okay, there we go. And then my dimension should come here. Okay, thank you. Okay, so here's my new byte array, yay long, and what I'm going to do is come in here and let's start populating this array based on distance. So I'm going to run a series of if statements, if distance, and we happen to know that the value out of range is going to be 0, so I'm going to say something like this. Let's sort of break down the distance into how about from 800 to 2000, 2000 to 3000, and 3000 to 4000. So which basically means, let's break it down as if distance less than 2000, do something else. If distance less than 3000, do something. If distance less than 4000, then do something. Actually, I know I have an if statement that handles the 0 condition. Distance less than 800, do something. Not 8,800. So this is the situation where right, and then everything else is going to be sort of steps. Okay, so if distance less than 8,000, then I want to populate. So my new color array is what I want to populate. When I say new byte, by default all the values are 0, right? So what I'm going to do is I'm going to populate them in terms of red, green, and blue channels, or blue, green, and red channels, because I know blue gets stored first, green gets stored next. And that's why I create this blue offset, green offset, and red offset. So the way I'm going to do it is, let me show you what I'm doing. So say for instance, if somebody's really close to the connect, I want them to be painted in blue. And if they get a little farther away, I want them to be painted in green. And if they get a little farther away, I want them to be painted in red, right? So the way I would put it up is probably something like color of color index plus blue offset equals 255, right? Which basically means of the 4 bytes that denote the blue, green, red, and blank pixel, I'm just choosing the blue pixel alone and filling that with a channel of 255, which means it will make that whole pixel light up in blue. So I'm going to basically do the same thing here, but instead of blue offset, I'm going to say green offset and red offset. The reason I use these offset colors instead of just saying +1 or +2 is for readability, obviously. That's all I'm doing. I'm adding +1 or +2, but for readability, it kind of helps. So I think that's it. So what's happening now is, let me remember to increment my color index by 4, because for each pixel, I'm jumping 4 pixels, right? And then what I'm going to do is I'm going to come in here, I'm going to say image2.source equals blah, blah, blah. All of this is fine, BGR is fine. Except now, here, I'm going to have it render the color array. And I know that pimage.bytes per pixel, because it's a depth map, would have normally returned 2. But I'm using a BGR32 format, 4 bytes per pixel, so I'm going to manually choose 4 here. But I think that should basically be it. So let's walk through what we're doing. You know what's funny is, I think that's it. Yeah, let's walk through what we just did. Quick summary of what we just did. For depth frame ready, we did the exact same thing as before. We read the image frame and got the image from the image frame. But instead of displaying it directly on the screen, it was resulting in mostly a super dark image. What we're trying to do is basically read the distance value for each pixel, and based on the distance value of each pixel, we're coloring that pixel. So what it's going to basically do is give us a histogram, if you will, on the screen. All the closer objects will appear blue, slightly farther off will appear green, and far off objects will appear red, and anything beyond that will appear black. Right? So that's basically a color-based histogram that we're creating. And so let's see what happens. erroring out. Okay, what's the problem? Maximum index was outside the bounds of the array. Okay, let's see. Color is a byte array, and it is 76,800 long. Color index is already at 768. There's some problem somewhere.
Size of times 4.
Times 4? Exactly. Thank you very much. So now, hopefully, okay, there it is. I think it's working. So let's do a quick test. So if I'm super close, right? You can see my hands here, but the depth sensor cannot read my hands because it's less than 850 millimeters. If I keep coming a little farther, my hands will become blue, or I'm actually blue. So what this means I'm between, let me see, okay. At this point, I'm between 800 millimeters or so. Now if I move a little farther away, from blue I should become green. There I am. I'm blending in with this. In fact, let me turn it this way. Let me turn it towards you guys. This is a pretty beautiful histogram, right? I mean, first row, if I came sat in the first row, I'm all blue. Next row is all green. The row after that is all red. And the row after that, from there on to the end, is all black. This is a simple color-based histogram of the depth data. Yeah? And it's, even though it seemed like it took us a long time, I hope you see the code is pretty simple. And this is where, at this point is where it will be super helpful to sort of use frame numbers and timestamps to coordinate. If you're doing especially something to coordinate between the vision camera and the depth camera, that was the time to use those to sync between the two. Right? How many doing on time? 3:40 to 20 minutes? Okay. 20 minutes? So great, and I think we have 20 minutes, so I think I'm going to step it up a little bit. I want to show you one more demo, actually. So what I'm going to do is I'm going to move this slightly closer. So right now, I want to show something. When I stand in front of it, obviously under a meter, I'm all black, blue, green, and red, and black again, right? But here's the point. At no point does it do any sort of human detection, right? It's basically just doing basic depth map information. I think the next step I want to show you really briefly, and this I think is very exciting. This is going to be the feature you'll probably end up using the most in the Connect, is instead of just using depth, I want to show you how you can use depth and player index, right? So that's the only change I'm going to make here. And then there's one more change I have to make. In depth stream.open, image type should also be changed to depth and player index, right? This is the only two changes that we need to make. Everything else, the depth frame ready, everything else can stay the same. Now here's the problem though. If I ran this as it is, let's run this as it is. You see this, our histogram channel is broken. It's really not showing anything, it's all showing black because none of the distance ranges are working well, right? It's not working properly. Anybody know the reason why that is? Because all the values that we're getting are greater than 4,000, right? Because what's happened now is when we sort of, let me go to slides for just 1 second. Okay, the first time we ran this, we just used depth alone, which means data was only represented in 12 bits, which means when we reversed order and left and sort of ordered, when we left shifted and ordered, the values were between 800 and 4,000. When we use depth and player index, we use 12 bits, but we also use 3 bits to identify the user, right? So what we end up actually doing is we end up using 15 bits, right? And so when we left shift and OR, it basically results in a number close to 32K or something. So that basically means every number is greater than 4K, and therefore it's all black. So that aside, what I think I want to do now is basically code up the application to use depth and player index, which means I want to use the 12 bits. I want to extract the new 12 bits. It's not in the last 12 bits anymore, it's offset by 3. I want to grab those, and I also want to grab the last three bits, because this is going to give me the player index. So let's code that up. It should literally take us about 4 or 5 lines of code. So let's code that up. First, let's fix the get distance method, because this is not going to be the formula anymore to grab the distance. I'm just going to copy paste it so I can make small changes. Now here's what we did earlier. Earlier we just sort of flipped it and ORed it. P1 has 3 digits of segmentation mask, which needs to be thrown out before we can OR it. So to throw out the last 3 digits, what I'm going to do is I'm going to right shift this by 3. Right? So what this is going to do is going to take the last 3 digits and throw it out. Now here's the thing. I still need P2 to come all the way to the left before I can OR it. But how much do I want it to come to the left? 5, exactly, right? Because P1's moved 3. So instead of making this come 8, I only need it to come 5 because this is already moved right by 3. So exactly, right. I mean, if I just make it come by 5, this is my new formula for getting the distance with the segmentation mask turned on. Now if I run this, I think it should be fine. So I'm all blue, now I'm all green, now I'm all red, now I'm all black, right? So fantastic, our app works like before. So that's the only change in formula you need to make. The reason I'm showing this is when you often look at connect samples, you'll see either this formula or this formula, and you need to sort of understand why people are bit shifting left and right and all of that. Once you get that, you're done. Now here's the really interesting part. You know how we're basically doing the measurement here? Let's basically do something like so. I'm going to basically now extract the last 3 bits from P of I. If P image dot bits, isn't that what we're looking for? P image dot bits I, right? If the lower order bits last 3 digits, and the way I look to see if the last 3 bits are set is by ANDing it with 7, right? So 7 is 1, 1, 1 and all zeros, right? So now if I take any number and if I AND it with 1, 1, 1 and all zeros, it basically just extracts the last 3 bits and gives it to me. So instead of doing an if, let me do this. Let me switch on. Let's assign somebody ID 2, right? Or it detected a second human shape. It doesn't have to be concurrently 2 humans. It's just detected somebody in as player number 2 is what it is. So let's just see how it is. Now, if a person is a human, let's color them differently. Let's color them. Right now we're using black, blue, green, and red. Let's use white maybe, where for white I need to take the red. I have to basically make everything 255. So green and right, okay. So the first player it detects is going to be all shown up in white. And how about the next player it detects can be all shown as, what is red and green, or green and blue? I don't know. How about maybe, let's just do 128 to everything, so there'll just be a shade of gray or something, right? Okay, so now here's what I expect. When I run the app, it's gonna run just fine. When I walk in front of it, it's gonna work just as before. Right now I'm blue. But if I move a little bit back, as soon as it can see my knees, it'll detect me as human, and instead of me becoming green as before, I should turn white, right? If the detection thing works. So let's see. I walk a little bit, I become green, and I became red, which is weird because that means the detection didn't work. Let's see why.
Color index. Color index. Color index.
Color index, thank you so much. You guys are helping me a lot, seriously. Okay, and let's do this. This would have been pretty cool. The top left pixel alone might have been white and everything else would be the same color. Okay, let's try this again and hope that it works. I should be blue. If I step back a little, I should turn green, and now I think I should turn. I should have turned white at this point. Come on. Okay, help me figure out what went wrong. Let's see. Okay. Is it? The flags right here? Oh, you think it's initialization flags? Actually, if that had been a problem, it wouldn't have run even, right? Let's see though. Okay, so the initialization, it's depth and player index, then when it's open, I'm just gonna do, I want depth, I've got depth and player index, depth frame ready, that's fine. And depth frame ready, I come in and check for the P image, all this is fine, this is fine. You know what, let's do this. Let's set a breakpoint. Let's set a breakpoint. I wanna see what happens here. I wanna see the result of this. So I'm going to set a breakpoint here to see if the code ever falls. Well, it's always going to fall in 0. Well, yeah. I don't think the code ever gets in here at all. So let's F9 it. Let's see if the code gets in there. I don't think it does, but. Oh, wait, something happened. I became gray. How is that? And see, now I can go up or down or whatever. And it lost the player, and now it came and fell in here, which is really, really weird. Because now it's working. Hello? Okay, let me remove the breakpoint. And maybe I think I should face the connect and walk. So you guys can tell me if I become white, because I think my face is turned away. Okay, I'm going to face. This is the buggiest piece of code ever. Okay. All right. We're going to do one last code review and see what the problem is. Because last time it fell through. Okay, so what are we doing? Yes?
The index is not crucial. Sometimes you jump into index 5.
Yes. I can't believe I didn't think of it. Thank you so much for that. So basically what's happening is because I used a switch, I'm only checking for 0, 1, and 2. Let me do this. I'm going to default it. Because the value, like we said, is going to be between 0 and 6. Oh, 10 minutes. Okay. The value is going to be between 0 and 6. We're only looking for 0, 1, 2. In all the other cases where it's, where the value becomes 3 or 4 or 5, we're just basically not doing anything, which is what, thank you so much for that catch. Now if I default it, worst case scenario, if I'm not even detected as number 1, I'll still end up becoming gray as soon as it detects a human character, right? So, let's try it again, one last time, there it is, I became gray, which is fantastic. Now I can walk wherever, and now I'm player 1 again, haha. When you go out of the frame and when you come back in, it will detect you as, see now I'm gray again. So this is a way for it to keep, what's happening is it will keep assigning the next player number, now it should become gray. Okay, 1 out. I think I have to do a lot of grays now because, for 4, 5, 6, and now if I keep doing this, ultimately I'll become white. It's a good workout. animation. But here is the really cool part. Shall I show you the really cool part? Here's the world's cheapest green screen technology if you want. If I comment out all of this, oops, what did I just do? Okay, the world's cheapest green screen is as below. Okay, if I just Control X that. You see, it completely segments the background out, and it only presents the human. So what you can do at this point is you can render whatever background you. Does that make sense, what I just did? So this basically is the simplest way to achieve green screen functionality using Connect. So since the background is completely black, and since you are generating it, you can throw in whatever image you want. And one of the best ways to do it is if you take if you have an existing image that you want to overlay as the background, you can actually use a class similar to bitmap source and actually break it down pixel by pixel and read the color image pixel by pixel. And in this code, where we are generating random colors, you can actually substitute those colors, right? So it's a really, and it works beautifully actually. It's a really effective way to do green screen technology. And now somebody showed me I had 10 minutes left. So what I'm going to do is I'm going to basically show you 5 minutes left. Okay, I'm going to show you one last demo with skeletal tracking. And if I show you that, I've pretty much shown you everything there is in the camera aspect of things. To turn on skeletal tracking, it's very simple, right? Just like how we turned on color and depth and player index, I can just say or and do runtime options dot use skeletal tracking, right? And what this is going to activate is the whole skeletal tracking pipeline inside Connect. And since skeletal tracking is not a raw stream, I don't have to open anything, right? This just activates it. I don't have to open it. So what I can do now is I can come in and directly handle the event for skeleton frame ready, right? Just like for video and depth frame ready. And I'm just going to say plus equals tab will generate the new event handler for me. And let's come in here. And let's look to see how similar the code is. In the past, we would get from E, we would get image frame. Now if I do E dot, you see I get skeleton frame, right? So I can do things like skeleton, and skeleton frame is of type skeleton frame. So I can do things like skeleton frame, S frame equals E dot skeleton frame. And if I see what I get from S frame, you see I get this collection right here called skeletons, right? I also get a bunch of other things. I also get things like, the frame number and timestamp as before. If I want to synchronize skeletons with the other subsystems, depth and video, I can do that. I also get something called the floor clip plane, which basically, so when Connect looks at skeleton tracking, it tells you, it has to identify where the floor is, and the skeleton is sort of the normal from the floor. So in sort of an angled situation, Connect will tell you which is the floor clip plane. So is it like a horizontal plane, is it vertical? It's like an angled plane and stuff like that. So if you're seeing errors in skeletal generation, and that is because of a situation like this where it's a non-flat surface, then check out floor clip plane. But for the most part, you don't have to worry about this. And finally, you get something called quality, which basically tells you the quality of skeletons generated, which we'll look at in a second actually. But the most important attribute here is the skeletons collection. So what I'm going to say is, let's collect that in a skeleton data collection. I'm going to call it all skeletons equals sframe.skeletons. Now, when I have a collection, I can always run through it. Now, by default, the Connect, just like the depth frame, can identify up to 6 humanoid characters on the scene, and it can make 6 skeletons out of the 6 humanoid characters. So I'm going to run a for each loop for actually let's just do a for each. for each skeleton data in all skeletons. So at this point, it's going to look for each skeleton. Now, here's the interesting part. Whether or not it sees skeleton data in the front of the sensor, it'll return 6 skeletons, right? The way you determine if it actually is seeing a skeleton or not is by checking for skeleton.tracking state. Because the tracking state is going to be one of these options. Not tracked, position only, or tracked, right? If it doesn't see any skeletons, for all 6 skeletons that it returns, it's going to say not tracked. If it sees skeletons in front, if it sees a human character that it can skeletonize, it will basically set the tracking state as tracked. But if it sees more than 2 people at the same time, then it cannot do skeletal tracking on more than 2 people. So if it sees, I don't know, 4 people in the scene in front of it, for 2 people, it will return a state of tracked, and for 2 more people, it will return a state of position only. Does that make sense? It will track the positions of up to 6 people, right? Where you are in terms of X, Y, Z. It'll track one position of the center of gravity of your spine for 6 people, but for 2 people, it'll give you 20 joints across your body, right? But since I'm only interested in tracking one person, I'm just going to look for a position of track. So I'm going to say if skeleton.tracking state equals skeleton tracking state.track. So at this point, I can grab from the skeleton collection a bunch of things. I can grab the overall skeleton's position, right? Whether or not they're tracked or just position. But if they're tracked, I can get their entire joints collection. So if you look at joints collection, you see all these 20 joints, ankle left, right, elbow left, right, foot left, right. I can get this whole collection. So I can do something like, I can get the head joint, and from there, I can grab the position of the head. And it's going to return the position in X, Y, and Z. The interesting thing to note is while the depth camera returns position in meters, the skeletal tracking returns the depth camera returns the position in millimeters. The skeletal tracking returns the position in meters, right? So you will get the value between +1 and -1 for X and Y, like between +1 meter and -1 meter for X and Y, and Z will be all positive because you're in front of the connect the whole time. So I'll show you a quick example of what I'm talking about in the next 2 minutes. So instead of all of this here, I'm going to go to my toolbox, drag a canvas. I'll show you why I'm using a canvas, because a canvas is easy to create positions with. Okay, now let's go into properties of the canvas, set the background to a solid color, like yellow or something. And let's create 3 ellipses. This is one of the easiest kind of tracking demos. I'm just going to do this. So what I'm going to do is I'm going to have connect, not just, we saw how it could track all of me and bring things up. I'm going to take 3 more minutes of your time, even though we're officially out of time. We saw how the Connect can track all of me, but it couldn't make out where my head is, where my shoulder is. Now we're going to do that. Now we're going to basically have Connect see me, but then break me down into my head and my hands. So my goal is going to have this ellipse follow my head, and these 2 smaller ellipses follow my hands. That's the goal, okay? So let's go into the code. Before we go into the code, let's call these different ellipses head. This ellipse is going to be left hand maybe, and this should be the right hand. Okay, sweet. Actually, it should be the reverse, I think. It doesn't matter. I mean, the ellipses can travel. Okay. So head left and right. Okay. So what I'm going to do is take the position of my head, and if you look at what position sends out, it sends out a bunch of things, but most importantly, it's X, Y, and Z. You might be wondering what W is. W is a probability measure of between 0 and 1. the value of W can be between 0 and 1, and it's the probability estimate that Connect is sending you of the position of that joint being at location X, Y, and Z. So if it can see that particular joint, if it can see the head in this case, it'll assign a W of 1, right? But if it cannot see my head, it can only see neck down, it'll still return an inferred XYZ, but the probability will be lower in terms of what the calculation accuracy it estimates it to be. So this is very valuable in terms of figuring out if Connect is just guessing at a value or Connect can actually see the value in person. But at this point, I'm not going to worry about W, so I'm just going to take the X and the Y. So what I'm going to do is this. I'm going to say head, or actually I'm going to say canvas. And this is why I chose a canvas, because canvas supports two properties called set left and set top that allows me to take the canvas and position it, or that allows me to take the ellipse and position it anywhere on the canvas. So I'm going to say canvas.setLeft. And now I'm going to say the element I want to set left is head, and the value where I want the canvas to be is skeleton.joints joint area head.position.x. Okay, before I do this, instead of making the code too complicated, let me talk about one small thing. Okay, the value, like we said, of x that you get back is actually in meters between +1 and -1, depending on if you're to the left of the Connect or right of the Connect. Now, that doesn't really translate very well to the canvas resolution, which could be like 500 pixels by whatever, right? So the Connect runtime offers a very cool method called, in Connect.skeleton-engine, there's this very cool method called skeleton to depth image, right? If say for instance, you don't really care about the actual dimension of +5 meters or -5 meters, if all you care about is where is the head as it relates to the 320 by 240 depth image, you can use this method, right? And you will almost always use this method if you want to take skeleton tracking and show it on the screen for whatever reason. So I'm going to say skeleton to depth image, and you can basically see that it takes 3 values. It takes a vector for the exact point where the head is. It also takes 2 parameters, depth x and depth y, which are out parameters. You'll see it says out. Out means that the value will get returned in these. You know how a method or a function can only return 1 parameter? But using these out parameters, these are by reference parameters, if you will, where we return multiple values. So I'm going to show you how to use it, right? So I'm going to say float dx dy, and then I'm going to basically come in and say my location that I want to convert in a second. This is all going to make sense. Okay, so this line hopefully should make sense now. What it's doing is I'm using the skeleton to depth image call to provide the position, the actual position in meters of my head, and I want that converted into dx and dy as it relates to the 320 by 240 pixel. Now dx and dy are going to be a floating point number, as you can see. It's a float. It's going to range between 0 and 1. It's going to tell me at what percentage of the pixel is my head exactly at, right? So it's going to be between 0 and 1. So to get the exact position of where to place my head on this canvas, I'm going to look at this canvas right here and see that the height is 239. I'm going to make it 240 just for the math to be simple. Unlock. I'm going to make the height as 240 and the width is 503. I'm going to make the width 500. So now we have a 500 by 240 canvas. So what I'm going to do is I'm going to set the canvas.setLeft. I'm going to take my head position and move it to dx times x plus 500. And you sort of see where I'm going with this. Now I'm going to say canvas.setTop. The same head position should be at dy times 240. Right? So I'm going to do the exact same thing. I'm just going to copy paste this code, if you will, for my hand left, and I'm going to take this position and move it to left. Okay, and then once more I'm going to take this code and instead of head I'm going to do hand right, and I'm going to take this and move the light on us. Okay, I think that should be it. Let's make sure everything is in place. So if skeleton.tracking state is tracked, then we first do a skeleton.depth image, grab the position of my head, then move it out to dxdy, and then move the head ellipse. Do the same thing for hand left, do the same thing for hand right. Okay, sweet. Let's hopefully there's no errors. Okay, here's my canvas. Here's me, and when I move sufficiently enough so I can see about 3/4 of me. Okay, I should calibrate it a little further because my head is far too low. It's funny, you know, oh, actually my hands are above my head. It actually makes sense. So see, you can actually, and right now I'm sort of off-centered from the Kinect, so this is sort of the center. And so you see my head is there. So it's actually tracking. I mean, obviously you can assume that you have to fine-tune it a little bit in terms of scale and all of that. So right now it seems like I have to move my hands a lot. You're clapping already. You want me to end up, And what was that? It seems like I have to move my hands a lot to get small motions in my hands. So you can actually work on scaling issues for that. So for instance, if I say at 2 times scale, right? I mean, this is a very crude estimate, but I mean, if I say for my left hand and for my right hand, I'm going to say give me 2 times scale, which means if I move my hand even a little bit, it'll move it a lot. Oh, it's moved out of. So yeah, I mean, there's ridiculous levels of jitter. So, but you get the idea. So you can basically, in spite of the scaling issues, you can basically see how simple the code is, right? You can basically call the event handler. It'll automatically get called for you, and then you'll get 6 skeletons, and for each skeleton you'll get 20 joints, and for each joint you can get its position in terms of x and y, which you can then convert back into screen coordinates and put it back on the screen. So that's literally, and if you look, this is very similar to the way we did image, and depth frame data. So hopefully that makes sense. If you have any questions, obviously I'm happy to take, but this is all the content that I wanted to show. And this puts you in a really good position now to look at the sample code that comes with the Connect SDK and to look at all of the other projects that Stuart talked about and take it from there. So with that, I'm sorry I ran out of time, and I sort of turn it back to you to take it from there. So with that, thank you so much, guys.